I'm Russ Ropken, RSI company. My real goal here today is just kind of try to introduce some more object-oriented programming ideas to all of you. I don't have any products to sell or anything like that. I just hopefully get your mind thinking a little bit, maybe give you some different ideas on how you might program and how you might organize some programming. So today we're going to talk mostly about visualization and the underlying code that feeds this visualization, with the whole goal to be able to create an I/O handling routine that I can use for any CODESYS-based PLC. That's kind of the whole idea, anyway. So initially, showing the product map here, we're going to be talking about visualization, of course, and the runtime and communications between the two. So let's jump into the agenda. So as with just about any project I work on, there was an initial problem. So we're going to talk about that, how this project came about and how it evolved from that problem. And then we'll talk really briefly about what CODESYS visualization is, and just kind of give you a quick overview on that. The object-oriented approach that we took to reach our end goal there. And then at the end, we'll have a live demo. I actually want to show the code to you, kind of give you a quick overview of how we put it together and see it in runtime here on a simple little demo that I created. So initially, the problem. So came about winter of 2020, right? We had the pandemic going along. One of my clients was building a new water treatment plant. At that time, they had 7 control panels that we needed to start up. And lots of I/O, tons of hardwire I/O, a lot of Ethernet IP and Modbus TCP communications into these controllers. Now, we also had to deal with the fact that we had to limit the number of people on site, of course, social distancing, all of that stuff. So the plan was, all right, we can program this thing remotely. We had remote access. We can do all the programming we needed, but we needed somebody on site that could do the I/O checkout. And we wanted to make that I/O checkout as simple as possible for them, right? We didn't want them to have to install something crazy. We wanted to be able to walk up to a panel, bring up a program, and allow them to simply check out the I/O and get all of that taken care of. So that was the problem. How do we do this? So we needed a simple user interface that was preferably browser-based, right? So they didn't have to install anything. And from that, we also said, hey, while we're doing this, let's make this a generic user interface that we can use across the board for any CODESYS-based PLC. So that's kind of where the whole project came from. And of course, it has just grown from there, right? Now, this is just a list of the initial features for this project. So we want to support multiple I/O devices, hardwired Ethernet IP, Modbus. We also had some HART connected devices, and whatever else might come along, right? For the I/O, we wanted baked-in support for certain features. Control inhibit, at least that's what we call it from my background. But basically, be able to enable and disable the I/O. I want to disconnect the logic from that I/O point and be able to actuate an output, actuate a digital output, an analog output. Same thing on the input. I want to be able to disconnect the logic, not pass it on into the program, and be able to see that input coming in. I want to be able to do engineering unit conversion, of course. So for our 4 to 20s, we want to convert those to whatever engineering unit we need within the controller, and be able to change that and dynamically set that, because Even though the engineer said that pressure transmitter was 0 to 300 psi, we all know when you get there, you find a 0 to 150. So we want to be able to easily change that and pass that in. For digital inputs and outputs, we also wanted to support inverting because again, is it a normally closed? Is it a normally open? If we just invert it right at the I/O, then we don't have to worry about making a bunch of changes in the code to handle that. Just have a quick little checkbox, be able to invert, and away we go. And then, of course, we need data quality status. Is there something failed with this transmitter? Are we outside of our 4 to 20 range? Is the card failed? Maybe all of the I/O points are no good on that. So we need a way to monitor the data quality status for all of that I/O. And then lastly, as I've already mentioned, easy access. This is not a SCADA system. This is a commissioning tool, a troubleshooting tool. So it needs to be very easy to operate with no installation. And of course, simple, quick development and deployment. That's always important to get that taken care of. So, of course, we settled on CODESYS visualization for this project. It was pretty much a no-brainer, given that our controllers were CODESYS based to begin with, did support the CODESYS visualization. Very easy to use, both from a development side and a runtime side. It's built into the development environment, the IDE, and it supports any browser. So using the Web Visu side of things, any browser will be able to access this by hitting the controller directly. Not to mention, you also have direct access to the program structures and data in visualization. Makes it really easy to configure, and it's very object-oriented programming friendly. And we'll talk about that more when we get into the live demo and how that's implemented. But as you create those reusable symbols or structures that you use within your code, you can build your object-oriented visualizations off of those structures and tie the two together, and then reuse those symbols over and over and over again. So, like I said, we'll talk more about that part of it when we get to the live demo. All right. So lastly, the object-oriented approach here before we get to the live demo. So we created some structures that we build on for this system. Even Sam mentioned in his presentation the idea of extending structures or inheriting structures. And that was the plan we made here. So in our structures, we had a main level, a rack level structure that defined a rack of I/O. Underneath that, we had a module or multiple modules, right? The rack structure contained an array of modules. And then that module contained channels, which of course we ultimately mapped to our I/O. The rack and the module structures are intended to be inherited. So they have some base properties that we use on screen and within our code, but every PLC is a little bit different. Opto22 handles their rack and their module and how they present you the status information and things like that is different from a WAGO or PLC Next or whatever you're working with. So we built these so that they would have all the base information that we needed, and then you could inherit those and extend them for that specific data that you need for that particular device was kind of the idea. The channel structure is pretty well set. That one does not change from manufacturer to manufacturer. It is multifunctional, so it'll work with an analog in, analog out, digital in, digital out. all of the standard things you would expect. We included some strings for defining the loop number, giving it a description, of course, the engineering units, and then the spanning details. So the raw 0, the raw span, the engineering unit 0, engineering unit span, so that you can convert that particular value into a real engineering unit value. And as I said, we're going to dive into the code, and you'll get to look at this a little bit closer. Also notice that the module has two arrays. One is channels. That's the end result. So that's the data that you're going to grab and you're going to use within your program. The raw IO array is the connection to the hardware. So that's the mapping point where you pull in your data. And notice it only has two properties, a digital and an analog. So if you're connecting to an AI or an AO, you use the analog. And of course, you use the digital if you're connecting to a digital type module. So that's kind of the general structure of how we laid this out. And then, of course, we wrote our programs around this so that we could use this with any PLC and be able to do quick deployment of a system and quickly commission that system. All right. So that's pretty much it for my presentation. I don't really care much for presentations, by the way. I'd rather dive in and look at the code. But real quickly, this is my demo system that I have running on my desk, just so that we have something to experiment with. My CODESYS controller is a Raspberry Pi. To that, I have an Opto22 Rio MM1. That is my I/O module, if you will. The Rio, which I'm sure Dan is going to talk about right after quite a bit, so I won't try not to steal any of his thunder, but this particular model Rio has 10 channels that are software selectable, can be analog input, analog output, digital input, digital output, and there's some restrictions on each of the individual channels, but for the most part, you can software select what each channel does. I had one of these on my desk. I figured it was perfect for this demo. And so the way I've set this up, I've got an RTD on channel 0 giving me ambient temperature. And then I've got a thermocouple to give me another temperature. I put in a couple of potentiometers to give me some voltage inputs just to simulate things like a pump speed or a flow or something like that. And of course, we have a couple switches. And then we have some outputs that aren't really doing anything, but that's what they're there for. So this was just my general test setup that we could experiment with and kind of show you how this all hopefully comes together. I will point out that the Rio, by the way, does support running CODESYS directly on that device. However, I chose to use the Raspberry Pi because it supports visualization, whereas the Rio does not. The Rio does have some other options for doing visualization and doing all kinds of other functions. But for this particular demo, the Rio is simply an I/O block to show that data. All right. Now, let's switch over to the visualization, and we'll show you the result here first, and then we'll kind of dive into the code. So this is my visualization running in a browser, connected directly to that Raspberry Pi. Initially, here we've got just some controller information that we're collecting. And this, by the way, is another structure that I didn't show in that diagram. But it's a controller structure that gives me the ability to give it a description, give me the IP addresses, what model it is, how many I/O slots it has, things like that. I also threw in the memory and CPU usage and the CPU temperature. I'm actually pulling that from the Raspberry Pi operating system. And of course, every controller has different ways to get that information as well, but it's typically available and nice to have, right? Just to give you information about what's going on with this controller. We also have the real-time clock down at the bottom, and then some project information about what's running on that controller. So now the I/O, and as I said, we'll show you how this is built. I don't know if I zoom in on this, if it'll make it a little easier to see, but we can certainly try. Make it a little bit bigger, maybe. So in this situation, notice that the controller back on the first page has 8 I/O slots. So when I go to the rack, I see all 8 slots. Rack 1, or slot 1, by the way, is the only one that's in use right now. And it's showing each of my channels, of my 10 channels here. Tag ID, so that's my loop number, description, units, the type, and so forth and so on. What's most important here is I can see what's going on. I can see the raw value. In this case, my RTD is at 1084 ohms, and I can see my engineering unit value, which is 23 degrees C at this time. And of course, if I grab, I think I'm grabbing the second one, the thermocouple. If I grab a hold of that second one, I can increase the temperature. And the other point I want to point out here is this control inhibit checkbox. If I check that, you'll notice that the in, that's my hardware input, is continuing to go up, but my value is not. So I've essentially separated this I/O point from the control logic, from the program within the control, and it's continuing to move up. And of course, I can certainly change this too if I wanted to plug in a new number and say it's 27 and hit OK. And then, of course, that's going into the program and being used this time. So this can also be used to do some testing on the program side if you want to move things around manually. If I uncheck that, we should go back into normal and away we go. Similarly, for the outputs as well. This output's currently on. And of course, if I click on that, I can take it out of control, or I can put it in control inhibit, and then I can write to the output and turn that output off. And of course, if I uncheck that, it'll go back to normal. I can also invert inputs or outputs for that matter. If I invert that one, notice that input's actually driving the running output, right? Same thing with any of those, simply check the invert and they will invert. All right. So the whole idea here, though, was each of these channels is a structure, right? And when we get into the code, I'll show you how each of these channels was built. This is a single symbol that I replicated actually 20 times because I support up to 20 channels per module. In this case, it knows that there's only 10 channels, so it only shows the first 10. And then based on the type, it changes how that particular input works. As an example, I could, now this won't change the underlying code, but if I made that input think that it was an analog input instead of a digital input, you can see that the data changes, thinking now that it's an analog input, and it's actually in a failed state. My code goes to a 1, meaning that I'm out of range. And I don't have anything wired to that input, so that makes sense. And of course, if I change that back, we'll get back to normal and see that data. Now, we also, as I mentioned in the beginning, we're showing hard I/O here. I also mentioned that we wanted to support all of the Ethernet protocols, Ethernet IP, Modbus TCP, as well as whatever else might come along. So I have a couple valves here. Now, these are simulated. They look to be, I'm going to have to change the zoom back so you can see all of it. They're Rotork based valves. Now, these are running in another PLC sitting on my desk. It's just simulating a Rotork valve. And we are talking Modbus TCP to it. But the whole idea here is kind of similar to the I/O. I want to see what's coming in. I want to see what the program is seeing. So on the right-hand side is what's coming in. The left-hand side is what the program is seeing from that data. Again, I can control inhibit. So if I control inhibit this valve, I have now separated my code from the hardware. And right now, let's see, this valve is opened. Let's say I take it to 50%, which is 500. We should see our valve moving. It's running closed right now, and our position is right there. We've made it to 50%, and we look good. So you're able to separate that valve from the logic, be able to write to the values, see it move, see it work the way it should. And then when you're done, you uncheck control inhibit, it goes back to the program, and now you can see we're running open again and moving our valve around. For the Ethernet-based devices, this is a little less generic than the I/O. I've created separate but similar structures for different valves. So, for instance, a Rotork valve, an Alma valve, and then the same for other objects, VFDs, so forth and so on. And then created these screens specifically for each type in that case. So we actually have two valves, an inlet and an outlet. And then lastly, just to help everyone out, I put just a simple process display screen to kind of show what's going on here. In this case, we've got our inlet valve opened. Our outlet valve is at 50% in manual. And then here's our pump. And of course, if I move the potentiometers around here, we can see the VFD speed change based on that potentiometer value. And then the second one runs flow, so we can see our flow move around. There's no actual logic behind any of this right now for my test system. I'm purely just bringing the I/O in and then displaying it so that you can see it. All right. One last thing I want to show you here before we get into the code. So as I said, this is a kind of a dynamic system that looks at the underlying structures and evaluates them so that it knows what to display. So if I go to another slot, that slot's not in use, it says it's not in use, and that's going to be true all the way down. But if I quickly change the code here, and I've got something in my clipboard, hopefully, and I'm going to jump over to the code just for a minute. I'm going to go to my I/O global variable list, and I'm going to tell it now that slot 1 is in use, and it's a 12-channel DI card as opposed to a multifunction card. So we'll just dump that in there real quick. Let's compile that and download it, and then we'll see how that changed that visualization. Let's do a full download. And hopefully that doesn't take too long. We don't want too much dead time. All right. We're almost there. Jump into runtime mode, and then we'll switch back to our visualization, which is back up and running. Switch over to rack 1. We still have our first slot, slot 0, which looks good and is still functioning, I hope. Yep, I can move things around. And if I go to slot 1 now, you can see I have a 12-channel digital input showing each of those channels. Notice that they're all failed. And that's because there is no module in slot 1 right now. So that module is giving me a failure, saying that it doesn't exist. So every channel has failed. But in any case, you can see that the visualization is built so that as you modify the code, add information, make changes, the visualization moves along with it. And we didn't have to make any changes to the screens at all to add that extra card, just the underlying code, and it showed up. So very good. All right. We're getting some questions too, so that's awesome. Can't wait to answer those later. All right. Let's look at some code real quick. See where I'm at in my notes here. I'm getting ahead of myself probably. Okay. We'll look at the structures first. So we'll start with the rack structure, and I'll zoom in on that so hopefully everybody can see it. The rack structure is pretty simple. Just contains a control inhibit. If I want to control inhibit that entire rack, I can. An error to let me know maybe I have a communication error with that rack, something like that, so I can enable that, whether it's in use or not, and then the number of slots and a few other settings for that particular rack. Now, as I mentioned, I extend this object. So if I go to my Opto22 folder, I have a rack Opto specifically for the Rio, and that allows me to extend the rack object. So this object gets everything that's here, plus whatever I add here. So there's my modules. Notice there of type module Opto. There's also this pointer. This gives me access to the module itself and the Opto object that gives me the information about that particular card or that module. So through that, I can tell whether that module is healthy, whether it's there, whether it's functioning or not. And then, of course, generate my error codes if I need to for each of those. Now, actually, I apologize. This is the rack pointer. If I go to the module itself has a module pointer so that I can get to that module. Now, the module, of course, contains the channels. So let's go back to the module. And there's my channels right there. And then here's my raw IO for that, for the data that's coming in. So that's where I want to head next, is how this actually works its way through the system. So how do we connect this data to the hardware? And then how does that data get from here to here, right? Because this is the actual object that we use within our code, and that's the object that we're displaying on the screen as well. So I'll try to make this quick, but I kind of want everybody to understand how we're getting from here to here. Now, if we look at the Rio itself, it's configured here, and each of the inputs are configured as an analog input or a thermocouple or whatever they might be. But if I edit that particular input, I have an IO mapping, and you'll see that's where I tie in to the IO. So for instance, this one is module 0, channel 0. So I use the IO array on the 0 element in that array. And then I tie to the analog or ANA property for that guy. If I look at a digital input, it's going to be very similar. The only difference being that I'm using the digital property on that. So that's how it gets mapped in from the IO, or from the hardware, we map into that IO array and pass that data in. Now, once that data is there, we have a program called main IO. Oop, wrong one. Main IO. Two things happen here. First of all, I call set rack IO. What that does is set those pointers for me that we talked about earlier. So I set the address for the Rio to that Rio IO. This gives me access in my underlying code to this object, my Rio, so that I can get the health of that particular module, make sure everything's good, generate any errors that I need to. So that's the first thing that happens. The second thing that happens is I should back up. There's actually three. So first of all, I have to get that pointer. Second of all, I call a program passing in my rack, and then I go through each module and check the health. So the whole purpose of this is to get the status of each module, whether it's in use or not, and also the feedback data from that particular module. So is it connected? Is it healthy? Am I getting data from it? So that first sets all of that. Then the third thing I do is actually process the IO. And that's that line there. So with that line, I will go through each of the IO points, grab the data that's coming in from the IO array, and then process that data. Now, I have to determine whether it's an analog input or a digital input, and then I have to handle all of the engineering unit conversion and pass that on. Now, from doing that, and we can jump in here real quick. Let's go to that real quick because it's pretty simple. As you can see, I go through each module and then I call another program. Let's process that module. And you'll see if when I go to that one, it's going to be very similar because I have to manage each channel. So in this program, I for loop through each of the channels. And then based on the channel type, I handle whether it's an input and an output, an analog or a digital. I take that data and put that information into the right spot on that particular structure. At the very end, I then call another program which handles all of the engineering unit conversion, as well as the control inhibit and all of those features. So all in all, it's definitely a layered structure, right? You work your way down through it. But in the end, each program itself is pretty simple and has a single feature that it takes care of. And that was kind of my whole plan. All right. So we now know that when I run this program here, it will take all of that data that's coming in from the hardware, and it will put the result in my channels object. So when I need to use that code or that value within my code, this is what it looks like. So if I need to access channel 0 on module 0 within my code, I can get access to rack 01, module 0, channel 0. In this case, I'm actually passing that to another program that I'm doing some stuff with. But if I need the actual value, I can just do value EU. That will give me the analog value. Value dig gives me the digital value. And then for analogs, I always add a value percent as well. So you can get the percentage of that particular value, which comes in handy at times as well. So that's how the data actually gets used within the code, is simply the rack, the module, the channel, and then whatever value you need from that particular channel. So as I said, the original goal here was being able to use this type of system for any PLC. And the trick to that is extending the standard objects, so the rack and the module, and then the code, of course, will change as well. So back over here, this process rack IO opto. If it was another manufacturer, I would have a separate program for that particular manufacturer. But in the end, that data ends up in the channels array with the same data, the same structure, so that I can display that information on a screen and use that information within my code, no matter what I'm connecting to or what the device is being used there. Okay, where are we at here? I got to look at my notes. All right, we're good there. We're good there. Now, let's talk about how this IO gets defined, because when I made that change earlier, I went into my IO global variables, and I made a change here and added another slot. So when you define this, now I've taken the practice of always creating an IO global variable list, and that's where I define all of my IO. Certainly not a requirement, but just how I've always done it, I guess. In any case, you notice I declare a rack at the top, and that in this case is an opto Rio rack. I have a couple properties that I set there, how many slots are available, whether it's in use or not. And then I define the modules. Underneath each module, I define each channel, its type, all of the information that's associated with it, the engineering units, all of that stuff gets defaulted by declaring it this way in the code. Any slot that's not in use at this time, I simply declare it as not in use. And then, of course, it won't get displayed on the viewer. Now, this might look a little daunting initially. I will tell you that I generate this code and originally from an Excel spreadsheet, which is not too bad, by the way. But there are certainly different ways to generate this code and make sure that it's consistent and not potentially cause problems. But once this code is generated and dumped in here, everything feeds off of this initial default values for these particular tags. All right, so that's how the IO itself is defined. And by the way, if we jump into runtime here, it does get laid out in a very nice tree. So there's my rack, there's my modules, and if I expand out module 1, I can expand out my channels, and there's channel 0, and you can see you get all of your good data that's coming in. Let's go to one that we can actually change here. There's our pump speed, and I should be able to move my potentiometer around, and you can see the raw value changing and the engineering unit value there as well. So it does get organized nicely in a runtime view so that you can see everything that's going on there. All right, let's log back out. Now, let's jump into visualization. I'm running short on time, but that's what this was all about. So the visualization, there's one main page, one main page that has a tab controller on it. Now, that tab controller is really driven from these individual tabs here. So here's my CPU. If we look at this, this object is simply another symbol that's linked in here. And that symbol has a reference to an object, which is right there. And we're going to see that throughout this whole visualization. Let's take a look at the hard I/O because I think that'll be most interesting. Again, I have a tabular control. Each of these tabs simply contain another visualization, which we'll take a look at in a minute. And notice that each tab links to a particular module. So at the very top, or at the top level, I have the rack linked in, and then each slot or each tab links to an individual module. So module 0, module 1, module 2. Every tab on this screen is using the same underlying symbol. So there's a single symbol for the module, and then you pass in the module that you want that particular symbol to connect to, and that's how it's all driven. Now, if we go to that module object, so I'll go down to visualization, I/O, and there's my I/O module. You'll see at the top here is all of the simple stuff. And then each of these objects, again, is another symbol that's driven from that module. You'll see that that one's channel 0, channel 1, channel 2, channel 3, on down. I think I supported 20 channels simply because that was the physical space that we had available mostly. So then if we dive down into that channel, this particular object, most of the stuff from here to the left is the same for every single object. For instance, the description is always there for every object. So that ties to channel description. Notice there's a var in out at the top here. I didn't point that out earlier, but that's the link to this particular object that's getting passed in to this symbol. So there's my channel. And then the variable here is channel.description. Now, the type of input will determine this last section, which one gets displayed. So there's a visualization or an invisible property on each one of these, and it's based on channel type. So if it's channel type 0, that one's displayed 1, 2, and 3. I believe that one is an output or a DI, that one's a DO, that one's an AO, and that one's an AI. So those are all just stacked on top of each other. And then the channel type determines which one is displayed at any given time. Let me throw those back up there. Again, all driven from that underlying channel object. So based on the type that's selected, that's what we show and display the correct information and allow to configure that individual channel. All right. I think that pretty well lines it out. We can take a quick look since we have a couple minutes. We'll take a look at the valve object, which I should have here. There's my rotorque valve. Again, if we look at our declarations up at the top, we're passing in a rotorque valve structure. And then I just build off of that structure. So if we look at our description again and our text variables, There we go. Data.description, and of course, IP address, and so forth and so on for each individual object. Again, this display is used for both valve 1 and valve 2, our inlet and our outlet valve. And we pass in, we look at that particular tab. This one should reference the inlet valve right there. And this one will reference the outlet valve. So reusing these objects over and over was the whole idea here. All right. Hopefully I didn't get too off the rails there, Chris, and I think we're right on time. And we'll pass it on to the next.
Yeah, thank you, Russ, for giving us a hands-on look at how object-oriented programming and visualization can simplify diagnostic and commissioning. It's always exciting to see what our system partners are building with CODESYS. Very, very interesting. Thank you very much, Russ.
Thank you, Chris. And I'll throw in real quick because I forgot to mention that code is available on GitHub, and anyone is welcome to go grab it. There's the project file there. I also use the file-based storage as well. So that's all up there. You can look at the structures. Everything's in GitHub at that link there on the screen. So thank you.